Everybody, if somebody will shut that back door. Devin, you mind shutting it? You're awesome. Thank you. Just a couple of reminders. One reminder, today we're having, tomorrow we're having a special seminar at 4 o'clock in Beauregard 104. Remember that was that suite that we used to have our class in over in Beauregard Hall before we moved to the... To what? Anyway, we're going to have this seminar. We're going to have a seminar over at 4 o'clock with Rebecca Adams. She's Nichols grad. She went away and she worked in industry for a while and she taught for a little bit. But I mean, she's, 26 or something. She's not that old. And now she's in graduate school at Tulane, coming close to the end of her graduate school. So, if you're thinking about medical school or thinking about pharmacy school or whatever, that's going to work out for many of you, but if it doesn't work out, graduate school is a nice option. It sets you up for a lot of nice jobs in Louisiana and around the country. So if you're interested in graduate school, then please come hear from Rebecca. She'll talk about her research. She'll also talk a bit about just sort of what it's like to be a grad student at Tulane. She's a really super person. You'll like Rebecca a lot. All right, they're having a lunch. It's mainly for chemistry students. But if you really have a strong desire to go, then like for chemistry majors, but if you have a strong desire to go, just let me know. I'm sure we can work through it. Okay? All right. You had a good weekend? Yeah. All right. We're going to start on chapter 4. But first, let's just do a couple of questions. Let's do number 6. I think this is exam 3 in the back. Exam 2, number 6. We'll do number 6 first. We'll just do a couple of these. Chapter 3 is really just a prelude to chapter 4. Do number 6 there. I do want to remind you have some OpenStax business due. It's due tonight. Oh, yes. And you'll have another one put up for chapter 4 soon, as well as a reading. Is the reading due tonight or the assignment? The reading's due tonight. Yeah. Homework Wednesday. Yeah, the homework's really the important thing. The reading, do what you do on that. Number 6 right there. If you finish number 6, you can go on to number 8. Doing pretty well. If you're uncertain about it, ask your neighbor. Your Ohm's law and your definition of current. Fundamental unit of charge, you'll need that. All right, we'll do about 10 more seconds. And stop at 2:10. 2:10. I think you have some similar questions to this in your AS, right? In your assignment that's due. So here we first want to find the current. I is equal to V over R. That's Ohm's law. V is 3 over 10, so it's 0.3 amps. But we're looking for the number of electrons that pass through the material. Remember, current, I could also write it as 0.3 coulombs per second. So I can find the total number of coulombs of charge that go through in 2 minutes, which is 120 seconds. So I say 120 seconds times 0.3 coulombs per second. That's what, 36 coulombs. But 36 is not the right answer because I'm asking for the number of electrons. So say 36 coulombs divided by 1.6 times 10 to the minus 19. That is the number of electrons in a coulomb. Or rather, I'm sorry, it's the number of coulombs in an electron. The charge of a single electron. And so if I do that, I get a really big number. A lot of electrons pass through in just those couple minutes. Now let's do number 8 now. Flat iron marked 120 volts, 600 watts. You ever seen that on your flat irons? Yeah? What is that? What is the resistance of that device? 120 volts, 600 watts. What is the resistance? I'm sorry, what? Oh, yes. Sorry, thank you. All right, let's stop at 45. So just 10 more seconds. 5 seconds. Let's see, I'm not sure. I think A is right. I'm pretty sure it is. I'm going to go ahead and mark it. So a couple ways you could do this. You could say, first, I want to know power. That's V times I. That's sort of our normal way of finding power. Though we had those other two equations, and I'll show you how to use those in just a sec. So I know that the voltage is 120 volts, but I don't know the current. However, excuse me, I'm sorry. I want to know the resistance. We'll come back. Well, we'll go ahead and find the power. 600 watts equals 120 volts times the current. And so that tells me that my current is 5 amps. And so if I know the current and I know the voltage, then I can find the resistance. So I say R is equal to V divided by I. V is 120 divided by 5. That's amps. I get 24 ohms. Or I could say, well, gosh, the power is V squared over R. And we have those three expressions for power. P is I squared R, P is V squared over R, P is VI, where you're just substituting Ohm's law into those equations. And so I can do this, and I get 600 equals 120 squared divided by the resistance, which is what I want to know. You can solve that for R, and you find that it's 24 ohms. Either one of those ways is okay to do it. I prefer the former, even though it's a little longer. All right? Not going to see a whole lot on Chapter 3 on the exam. You'll see, 3 to 5 questions maybe. But Chapter 3 is really important for Chapter 4 as we get into Ohm's law and applying that to circuits. But you will see power. You'll see resistance as it relates to resistivity, length, and area. And you'll see Ohm's law. Okay? Y'all feeling good for Chapter 3? Yeah? Okay. Let's move on to Chapter 4 then. Chapter 4 will get more into DC circuits, and actually this is our last chapter on circuits. We'll go into magnetism in the next chapter. I'll go through and do the homework for Chapter 3. And remember too, as you're doing the tutor assignment that's due on Wednesday, the homework assignment, that I pull questions directly from there for the test. I go through, when I'm making out the test, and I'll just find 3 to 5 questions. In fact, if you look at the old test, you can tell which one's from tutor, because back in the key it says, I think at S17 OS, I think is my key. Those are questions that I pulled directly from the tutor site. So I changed the numbers, but they're still the same. Work through the homework. Let's look at DC circuits. These are direct current circuits. This is in contrast to AC electricity. In our homes, we use alternating current, and we'll talk about this in the next chapter, but it gets down to how do we generate this current, and that has to do with magnetic fields. But the difference is that the alternating current, the current actually changes it looks like a sine function. It goes back and forth. It alternates from one value to another value, from say plus 1 amp to minus 1 amp. It's an alternating current, and likewise the voltage also alternates between plus 120 or minus 120 volts, whereas direct current is always the same. So that's like what we use in the lab. That's like what you get out of a battery. That's like what you use in your car. On some boats, they use DC electricity. So anyway, we're going to be dealing with DC electricity, but we'll find that the same will apply to AC electricity when we get towards the end of this chapter, where we look at our homes and how they're wired. All right, so first of all, I want to introduce the concept of electromotive force. We've already seen this, but electromotive force is just provided by a battery or power supply. So this is a source of electromotive force. We usually just call this EMF, and we usually use a script E. Looks like that for electromotive force. The reason that we use this, and you might say, gosh, this is really the same as what we had for voltage. The reason that we use this is just to introduce the idea of an internal resistance. So when you have a battery, you ever had a battery and you've hooked it up and it gets really hot? You ever done that? What usually does that mean about the battery if you have a really hot battery? Like say in your cell phone or elsewhere, like a rechargeable battery. What does that usually mean about the battery? Does anybody know? It's what? No, not that it's recharged. It's what, Lingley? Like if you're using it a lot, yeah. Also, that generally means that that battery is getting close to the end of its life. That if it gets really hot, the reason is that every battery and every power supply has a certain amount of internal resistance. Now, batteries are designed to have very low amount of internal resistance, but as they get to the end of their life, they develop more and more resistance to the flow of electricity. And so they have this source of internal resistance that gets bigger and bigger. And as my resistance gets bigger and bigger, well, the power that it disseminates increases more and more. Because as R goes up, then I just have more voltage that is drop across that resistor, and it just produces more power. That causes your battery to heat up. So batteries and power supplies have an internal resistance, R, which causes a drop in voltage. So for example, in this battery, the terminal voltage, that is the voltage, if you were to hook a voltmeter up to these two terminals, you would read, this as your terminal voltage. The terminal voltage is equal to the electromotive force minus the change in potential across the resistor. So I times R. Now remember, this comes from V is equal to IR. That's our Ohm's law. That's where this business comes from. Although now we're going to begin to talk about drops in potential and rises in potential. Now a resistor, which is something that you put energy into and it does something, it creates heat, or you use it to drive some mechanical system or whatever, you always see a drop in potential across a resistor. What about across a power supply like this, a source of power? Do you see a drop or an increase in potential when electrons go across something like that? Do the electrons gain energy or do they lose energy? They're going to gain energy, right. So as my electrons go through this, they gain energy, and as they go through this, they lose energy. And generally, this energy is lost to something like heat. So far, we've assumed that this internal resistance is 0, but now we're going to begin to consider that internal resistance. And you might have a couple of questions about internal resistance, and we'll get to that. We'll do some examples. But largely, it will work out in the same way that we've been working through circuits. We'll just use some slightly different terminology just to remember that these power supplies or these batteries, they have their own source of resistance. We'll talk a bit more about that later. Let's try this quick test. We have this battery, and ideally, it would provide 12 volts. However, when I have a current of 4 amps, the potential is 10 volts. That's what I measure across the battery. What is the internal resistance of the battery? All right, let's try to do about 10 or 15 more seconds. Let's stop at 1:15. Ask your neighbor if you're uncertain. Many of you have the right answer. We'll stop at 1:15. Just a few more seconds. All right. Okay, good. B is right. So I have this battery. Right, it's like this. It consists of a source of EMF and a resistor. I get an amp, or I get a current of 4 amps that travels through it. When I get 4 amps traveling through it, that causes a drop in potential here of 4 amps times the internal resistance. That's V equals I times R. That's the drop in voltage across that resistor. All right. Ideally, this would be 12 volts if I had no internal resistance. And so, really I'm getting 10 volts across it. So 10 volts is equal to 12 volts minus 4 times the resistance. That's just the equation I gave you previously, right? Delta V is epsilon minus I times R. And so I solve that for R, and I get R is equal to 0.5 ohms. All right? We'll see that more. We're basically using something we call the loop rule here, which we'll see when we get to multi-loop circuits at the end of this chapter. Go down from here, people? It's okay? All right. Hey, good job. Let's see, do we have all our softball players. Great job, man. Wait, it's 5 and 1 over the, or no, how many, you won 3, 4? 3 and 1? That was awesome. I think y'all have another game on Wednesday, is that right? 2 games, but at 5 o'clock? Yeah. Good job this year. All right, so each component of the circuit has either a drop and a rise in potential. And some components are electrons, or protons as we think about them. They gain energy. In some components, they lose energy. So in which components do they gain energy? The resistors are the power supplies or the batteries. Which do they gain energy? The batteries, right. Power supply battery. I'll call it a battery. And they lose energy in the resistors. So if I were to talk about the change in potential, I would say that this is plus the voltage, or plus E, if we want to talk about it in terms of EMF, though it's really the same as V. We're just sort of using these interchangeably. If I were to talk about the change in voltage for my resistors, I would say that this is equal to negative I times R. So I have a gain in energy or a gain in potential for my electrons going across the power supply, and I have a drop in potential across those going in resistors. And that energy usually goes into thermal energy, although sometimes you can harness it and use it for other things. But usually in a resistor, because of the type of element it is, that it's always going to thermal energy. It's kind of like your oven, right? If you have an electric oven, the heating element, it's just a resistor, right? Is the resistor in your oven, does it have a very large resistance, or does it have a very small resistance? Don't answer that. I'll ask it as a clicker question. So the resistor in your oven, does it have a very large resistance, or does it have a very small resistance? The heating element in your oven, a very large resistance or a very small resistance? Now remember, this is a high power device or a low power device relatively. It's very high power, it's probably a couple thousand watts. It's one of the highest power devices in your house. So ask yourself the question is, do high power devices have a big resistance or do they have a small resistance? Or you can think of the other way to think about this is, does the oven impart a little bit of energy to your food or a lot of energy to your food? A lot. It uses a lot of energy, and it uses it to heat up that box in your oven to cook food. So I need to know what resistance would give me the most energy flowing through that heating element? Does it have a large resistance or a small resistance? Y'all are almost evenly split, right? Like 30 and 30. Y'all ask your neighbor and see what they put. Because one of you is wrong. You want to get as many electrons flowing through that heating element as you can. All right, y'all moving in the right direction. I'm going to stop at 2 minutes. 8 seconds left. 8 seconds. Okay, good. B is right. Listen, next time you're at your mom's house or whatever, you're cleaning her up and you got down there and you say, gosh, Mom, this is a tiny little resistor in here. This is like less than an ohm, this resistor. And she's going to say, gosh, you're learning a lot down there at Nichols State University. Okay, so listen, those heating elements in your oven, they produce a lot of power. So remember, we did this was sort of the previous chapter, but P is equal to V squared over R. In your house, you have a constant voltage. So if you have a small resistance, I have a big power. You can think about it mathematically in that way. But think about it too that, if I have something that produces a lot of heat, then I'm going to need a lot of electrons to take that energy into that device. And I can only get a lot of electrons if I have a small resistance. Because if I have a big resistance, I'm not going to get many electrons because they resist the flow of electricity. Okay? What about in your hairdryer? Big or small resistance? Big resistance. In fact, look down the gun of the barrel of your hairdryer, and you'll see that it's just a coil of wire. That's all it is in your hairdryer. It's just a coil of wire. Nothing else. Nothing. It's just wire. It heats up really hot. Okay, so each component gives either a drop in rise or a rise in potential for the charges. So if I were to look at the loop, let's see. Yeah, so this is Ohm's law. V is equal to IR. So across the battery, as I said, we get a delta V equal to plus E. I've already written this, but just to drive it home. And across the resistance, I get a delta V of minus I times R. When you go around the entire circuit, the change in the potential is 0. So I like to think of this this circuit as like a roller coaster for electrons. And if you think about these electrons as they're going around a circuit, they come up here, they're coming along, and this is like the chain that pulls you up the roller coaster. You ever been on a roller coaster before? No? Yeah, some of you have. So it's like the chain that pulls you up and gives the electrons lots of energy. And then here it lets it go, and then woo, and they go through. This is the loopy-loop they go through. It slows them down a little bit, but they keep going. And then there's another loop-de-loop where they use up some energy, and then they come back, and then they go back up the chain, and then they ride the whole ride again. So they gain energy here, they lose energy in the resistors. It's like a roller coaster. So next time you're on a roller coaster, you can say, gosh, this is just like a loop in a circuit. Those electrons, man, they're having a good time. All right, so an electron at a particular spot in the circuit will have the same energy when it returns back to that spot. We can also write this as the loop rule. This is going to be called the loop rule, which we'll see more rigorously later. And the loop rule just says that the sum of all the potentials is equal to 0. And that is that I have plus E, that's for my battery, minus the loss of energy in my internal resistor, minus the loss of energy in the resistive element or my resistor out in my circuit, that this is all equal to 0. And this is called the loop rule. So if I wanted to solve for my EMF, for example, I could solve my EMF, it's going to be equal to IR plus IR. So my EMF, this is similar to what we saw before, but my EMF is dependent upon the current and the resistors that are in that circuit. Let's do an example. Actually, no, let's do resistors in series, and then we'll do an example. Let me just write down the rules for resistors in series, okay, and then I'll show them to you later. But for resistors in series, they have, this is only for series, they have the same current. The equivalent resistance is equal to R1 plus R2 plus R3 plus ... They, for resistors, this is true for all resistors, but Ohm's law holds. And then also for resistors in series, the voltage is equal to V1 plus V2 plus ... These rules should look familiar to you. I could also write similar rules for capacitors. I just want you to see them side by side, okay, because they're very, very similar. For capacitors in series, they don't have the same current, they have the same charge. The equivalent is different. It looks like this. You know, these are on your equation sheet, so if you forget, I'm sorry, that shouldn't be REQ, it should be CEQ. This is where students get hung up sometimes, so if you forget that there's this difference, look on your equation sheet, because all four of those equivalent capacitance, resistance equations are on that equation sheet. For capacitors in series, not Ohm's law, but we have something that, you know, I like to call sort of the equivalent of Ohm's law. Q is equal to CV. And then this same thing with the voltages, V is equal to V1 plus V2. That's also true. See how these rules are very similar? Have the same charge, have the same current. The equivalents are switched up, and that's unfortunate, but that's just sort of the way it is. Ohm's law, or this little thing which we don't have a name for. We'll call it, I don't know, Cap's law or whatever. And then the voltages add up the same way, for similar reasons. So let's look at resistors in series. So like we saw before, the change in potential here is equal to I R1 plus I R2. This goes back to saying, well, I see a positive change in potential, I see a negative drop in potential, another drop in potential, and adding all those up gives me 0. So that's where I got that. Did I say, oh, this is the chain on the roller coaster? This is the loop-de-loop. This is the loop-de-loop. And I add all that up, and I come back to exactly the same energy, so my initial energy is 0, and I'm just sitting there waiting for the ride to start. Did I tell you how we tricked our kids going up to the roller coaster? I told you that story. That was a good story, wasn't it? I'm not going to tell it again. All right, so anyway, so this is our change in potential is this IR1 plus IR2. I can rewrite this as I, just take out that I, R1 plus R2, and I get an expression for the equivalent resistance. So my equivalent resistance for resistors in series is just R1 plus R2, plus however many other resistors I have. Notice that the equivalent resistance is always bigger than any individual resistor. And that might seem like a duh, right? But we'll see that with resistors in parallel, that the opposite is true. That for resistors in parallel, the equivalent resistance is always smaller than the smallest resistor. But here, it's always bigger than any one of the individual resistors because it's just a sum. It's just a sum. All right, so to recap those rules that we have, resistors in series have the same current. The change in potential across the resistors in series adds up to equal the change in voltage across the battery. That's this rule, that V is equal to V1 plus V2 plus dot, dot, dot. All right, that the voltage that's provided by the battery is equal to the sum of all the voltages in a single series loop. Let's see, let's look at a scenario. Let's say I have these two light bulbs. What happens, these are in series, what happens if I remove R2? And then also what happens, well, first of all, what happens if I remove this light bulb right here? What happens to the circuit? Does it get brighter, dimmer, go out? Which is it? Yeah. It'll go out, right? I appreciate what y'all are saying, because y'all are right for the next question. We'll come to that. But if I take this one out, I break the circuit, right? I know what y'all are thinking, and you're right in what you're thinking. But right now, I'm looking for this answer. That as I have current follow up here, it goes through the light bulb. If I take this one out, then that causes a break in the circuit, and then everything goes out. So if I remove R2, everything goes out. Some of your old Christmas lights, they don't really make these anymore, but they used to be in series, your Christmas lights, and if you took one of the light bulbs out, the whole strand went out, right? Many of them are still that way, but we're getting more into LEDs, and they don't work the same way. And then if I replace R2 with a wire, what happens to R1? It gets brighter. So you can think about this. If I have 12 volts here, that means that when I had 2, I had 6 volts and 6 volts. We saw that with capacitors too, that when I had 2 identical capacitors, they split up that voltage between them. But if I take away one of these and replace it with a wire, now instead of having 6 volts, I have 12 volts across one light bulb. Y'all did that in the lab with the little Christmas lights. Alright, so let's look at this circuit. I want to know the equivalent resistance, I want to know the current through all the resistors, and I want to know the potential across each resistor. So don't forget your rules. I'll give you a couple minutes and you'll work on this. And then I'll jump in and show you. I'll sort of catch up. All right, so to find the equivalent resistance, you add all those babies up. So I say R is equal to 1 plus 2 plus 2. That's equal to 5 ohms. And so I can rewrite this as just a very simple circuit with 10 volts, 5 ohms. And then I want to know the current through R1. Resistors in series have the same what? Voltage or current? They have the same what? They have the same current. Resistors in series have the same current. And so whatever current is flowing through this resistor is also flowing through this. And so whatever current is here is also here, is also here. And so I can find that current, I, is equal to V over R. That's 10 volts over 5 ohms. That's equal to 2 amps. So I got 2 amps coming here, 2 amps going there, there, and there. So 2 amps, 2 amps, 2 amps. And then I can figure out, well, what is my voltage? Well, I know my current and my resistance here and here. So V then is equal to I times R. 2 volts, 4 volts, 4 volts. Notice that this all adds up to give me 10 volts. 2 plus 4 plus 4 is 10. And then also notice that the bigger resistors have a bigger voltage. So unlike capacitors, remember capacitors, if I have a big capacitance, I have a small voltage. That's not true for resistors. With resistors, if I have a big resistance, I have a big voltage. It's because I have this direct relationship between voltage and resistance. So given a current, if R is big, V is big. That wasn't true with capacitors. If C was big, V was small. So to sort of cement those in your mind, that they have these different relationships for between capacitance and voltage and resistance. One's a direct relationship, one is an inverse relationship. You'll probably see maybe one or two series circuits on the test, but mainly we'll have combination circuits. Let's try this one. I want to know the potential across the 8 ohm resistor. What is the potential across this resistor? Potential across that 8 ohm resistor. All right, let's stop at 135. Okay, very good. B is right. Yeah, that's right. All right, so I have 4 volts here. That must mean that I have 2 volts here, and I have 6 volts here. Notice how I thought about this is, I know that this voltage has to be twice this voltage, so if this is 4 volts, this has to be 2 volts. This voltage has to be 3 times that voltage. You see 12 and 4, there's a factor of 3, and so this has to be 6 volts, and they all add up before 12. Now, the way you do this, probably the way you do this, is you would find the equivalent resistance, REQ, is 4 plus 8 plus 12. That's equal to 24 ohms. There's 12 volts. So I say I then is V over R. That's going to be 12 over 24, or 0.5 amps. So each of them has 0.5 amps. So I say 0.5 times 4 is 2 volts, 0.5 times 8 is 4 volts, 0.5 times 12 is 6 volts. Why was the mother scared when her child brought home his report card? There were bees all over it. Oh. But that's my child, I know. All right. Y'all share your grades with your parents? Your parents see your grades? Yeah. You don't have to, you know. Like, there's a law, actually, in the state of Louisiana says that, but you should, because they love you. All right, so for resistors in parallel, I'm gonna write these down, but let's just sort of get the rules, just like we did for resistors in series. For resistors in parallel, they have the same voltage. Their equivalent is 1 over R1 plus 1 over R2. I'm going to write these again in just a minute, but just sort of have them all in the same place. V equals IR. And then also, the current is equal to the sum of the individual currents. the current going in equals the current going out. And now let's compare these to the rules that we had for capacitors, because you'll have capacitors and resistors on the test in 2 weeks. For caps in parallel, they also have the same voltage. The equivalent is the sum, not that inverse business. For these, Q equals CV. And then I told y'all this, but we don't really use this rule for capacitors in parallel. But the total charge is equal to the sum of the individual charges. But it turns out that's just not really useful, so we didn't really use that rule. But I like to have it just because, you know, it shows the parallels between these rules. Yeah. And it should be. Thank you. I made the same mistake before. Thank you. So this should be a CEQ and C1. Oh, shoot. I'm just going to write C over it like that. Thank you. All right, so notice the difference here that my equivalents are different, but largely they're much the same. All right, so for resistors in parallel, the potential difference across each resistor is the same. The current entering a junction must equal the current leaving. And this is what we call the junction rule. We'll use that probably next time, the junction rule. It says that if you have a certain current coming in here, it has to equal the sum of those individual currents. That is, I is equal to I1 plus I2. That sort of makes sense. If I have so many charges coming in here, then they split up. They have to equal what's leaving has to equal what's coming in. To find the equivalent resistance, I got 1 over R1 plus 1 over R2. And that's it. Do you want me to recap those rules again? Is that useful for you? Yeah. Okay, let's do that. Just write them down one more time, and hopefully that'll help them cement in your mind. So rules for resistors in series and parallel. You want to do the capacitors too? All right. I'm going to do like a big chart here. So for resistors, right here, in series. 1, they have the same charge. Same current. 2, the equivalent equals R1 plus R2. 3, V equals IR. And 4, the voltage is the sum of the individual voltages. So if I have 12 volts across 2 resistors, the sum of the 2 voltages across the 2 resistors has to add up to equal to 12. Resistors in parallel. They don't have the same current, they have the same voltage. The equivalent is 1 over R1, like that. 3 is V equal IR, and 4 is I equals I1 plus I2, plus however many there are. These rules number 4, this is the loop rule. Electricians use this a lot. And this is the junction rule. Right. If you go in any sort of circuits class, or if you take instrumental, you'll learn some of these circuits as well. All right. Let's just sort of recap the capacitor business. I know this is kind of dry, but it's useful to get these rules. Capacitors in series. 1, they don't have the same current, they have the same charge. Their equivalent capacitance is not the additive sum, it's just the inverse business. They have sort of their equivalent of Ohm's law, and the loop rule also applies for capacitors. All right, and then for capacitors in parallel, I'll give y'all just a second to catch up. I know I'm going kind of fast. All right, caps in parallel. They have the same voltage, just like resistors. It's just sort of the way they're laid out in the circuit. They see the battery the same. The equivalent, this is different. C1 plus C2. Put a little star by it because it's different. Q equals CV. And then finally, not a rule that we use, but Q total, that is the charge on the equivalent capacitor, is equal to Q1 plus Q2. Once you get these rules for resistors and for capacitors, the circuits are really just applying these rules. Let's do some. I go down from here? Everybody got that? All right, let's try this quick test actually. What happens to the equivalent resistance of a parallel circuit as you add resistors? Mentioned this earlier. All right, ask your neighbor if you're not sure. This is not intuitive necessarily, though, if you put in the numbers you see. All right, I'm going to stop at 43. Okay, good. B is right. The equivalent will decrease as I add more resistors. Let's think about this. If I have a circuit, and let's say it has 2 resistors. Okay, I have an electron, and it comes along here, and when it gets to this point, that electron says, I have 2 places that I could go. I could go here, or I could go here. Now, more electrons are going to go the easier path. So if I have a low resistance up here, I'll have more electrons that will travel this path, but I'll still have some party souls that go on this larger resistance path. But what if I add another resistor? Then that electron comes up here and it says, I used to have 2 paths, now I have 3 paths if I add a 3rd resistor. And says, well, that's a lot easier because now I have 3 different paths I can choose from. And likewise, if I had 4, 5, the more and more resistors that I add, then the more and more paths you get for that electricity to flow. So the overall resistance will decrease. As I add more resistors, the REQ decreases. As the number of resistors goes up, the equivalent resistance decreases. And then similarly, on a similar vein, the equivalent resistance is always smaller than the smallest resistor. So like if I have 3 ohms here, and I have 6 ohms here, then my equivalent of that, of a 3 and a 6 in parallel is what? It's 2, right? 1 over a 3rd plus a 6 is equal to 2. Notice that 2 ohms is smaller than 3 ohms. That as I add resistors, my equivalent will always be smaller than my smallest resistor. All right, y'all find the currents and voltages for each of these resistors. This one should be pretty quick. You might have a parallel circuit, but you'll just have one if you have one at all. That's just a straight up parallel circuit. What is the current and the voltage for each resistor? The total current and the equivalent resistance. Bless you. What's the voltage on R1? 10 volts, right. Resistors in parallel have the same voltage. So I'm going to have 10 volts here. and I'll have 10 volts here. Look, anytime you got two values, I can find the third one. I1 equals V1 over R. That's 10 over 2. That's 5 amps. I got 5 amps of current coming up through here. I2 is 10 over 4. Oh, that should be a B. 10 volts over 4 ohms. That's 5 halves, that's 2.5 amps. I got 2.5 amps going here. What's my total current? 7.5 is right. So I just add up those currents. That's my junction rule, by the way. Whatever current is coming out of this junction has to be coming into it. So I total equals 5 plus 2.5, which is equal to 7.5 amps. So that's my I total, that's my current I2, that's my current I1. Then if I want to know the equivalent resistance, that's where you do that funky thing. Was it 2 and 4? What's that, 2 fourths? That's 4 thirds, so 1.33 ohms. I'm sorry, ohms. All right, and then what was the other thing I want to know? Oh, that's it, right? But look, notice that I can double check my total current because I know I got 10 volts going across this 1.33 ohm resistor. So I can check my current. I total should be 10 volts, V divided by R, 1.33, and that's going to equal to 7.5 amps. So I can double check that if I'm uncertain that I've done it correctly. Just like with capacitors, you'll see lots of little checks that you can have along the way. This isn't that bad, right? These circuits? No. You know what? Next time they'll get a little bit more difficult, but y'all are going to be okay. We're just sort of building up to those, and soon we'll move on. We'll probably have a little bit of magnetic fields on our next test too, okay? Y'all have a great day. I'll see you